Hello, good morning, good afternoon, good evening, everybody, wherever you might be. It is my great pleasure to introduce my colleague from Denmark. This is already our third talk from Denmark and not the last one. Our speaker is David Kuv. I'm sorry, it's very difficult to pronounce all these Danish names like Szymanski, Nest. These are very difficult names to pronounce, but I'm doing my best. So it will be a very fascinating story of the non-commutative metric geometry of the quantum group SUQ2. David, the floor is yours, the Zoom is yours. Take it away. We are all ears.
Wonderful. Thank you, Piotr, and thanks for the invitation. It's a great pleasure to give this talk. I will do my very best to keep it fascinating, and should I fail, feel free to interrupt me and speed me up or slow me down if needed. As you can see, the topic is one of the all-time classics in non-commutative geometry, namely Bohdanovic's quantum SU2, and somehow the overall theme of the talk will be its geometry. And this is, you can take different points of view on this. You can either say this is extremely well understood because you have these differential calculi that were understood already in the seminal papers by Bohdanovich in the 80s. But you can also take another point of view, namely the point of view of Kohn and the spectral triples and all that stuff. And from that point of view, it seems much less accessible, the geometry, I mean. So I'm not going to solve this issue of modifying Kohn's issues into Kohn's axioms into a version that is suitable for quantum SU2. I think this is something that will require some more years of thinking, but I'm going to take a slightly more pragmatic approach in that I will ask, maybe instead of asking for fully fledged geometry, a spin geometry, maybe one can ask for a non-commutative version of a Riemannian metric. But before getting into the non-commutative Riemannian metric, I should tell you what a non-commutative metric is. And this is exactly what Riefel was thinking about back in the late 90s, namely, what additional data should I put on a C-star algebra in order to mimic non-commutatively the existence of a metric on the non-existing underlying space? And the resulting theory is the theory of compact quantum metric spaces. And Riefel was inspired by non-commutative geometry, as you will see in a second. And the definition of what is called a quantum metric space goes as follows. So not surprisingly, you start out with a C-star algebra, and we only focus on the unital, so the compact case throughout the talk. And then the additional data that you need to put on it is that of a semi-norm. And semi-norms in this line of business are a little bit special in that they're allowed to take the value infinity. But other than that, they satisfy the usual axioms of a semi-norm. And then I also demand that they interact nicely with the adjoint operation, and that L of x star is the same as L of x for all x in A. Now, the pair then, A together with the semi-norm, is a compact quantum metric space if it satisfies a bunch of axioms in increasing order of importance. So the first axiom just says that the semi-norm should vanish on the identity in the C-star algebra. And this is a very reasonable and mild requirement, and you will see in a second why it's natural to assume that. And the second thing is that this taking the value infinity is not getting too much out of hand. So I demand that the set where the semi-norm is finite is actually dense in the C-star algebra. And then here is the most important of the axioms, namely that if you look at this quantity quantity dl, which is defined on the state space, and you take two states and then you do the soup over all of the values that you get from letting the input vary over the semi-norm unit ball, well, the requirement is that this is indeed a metric. A priori, it could attain the value infinity, but we demand that it doesn't, and that this metric is supposed to metrize the weak star topology on the state space. And in this case, L is called a lib norm. So I'll refer to such a thing as a lib norm throughout the talk. So this is well, a slightly modified version of Rieffel's original definition. He was using order unit spaces, and here we're using C-star algebras, or maybe in a slightly more general setting where I allow for my A not necessarily to be a C-star algebra, but a complete operator system. So by that, I simply mean that you take a closed star invariant subset of a given C-star algebra, which also contains the unit. So I will actually need this added degree of flexibility, and it also has the property that it somehow fits well with the recent developments in non-commutative geometry, where Kohn and van Zuylichem are trying to get all of this stuff working exactly in the setting of operator systems. But if you're new to this, just think of A as a C-star algebra throughout the talk. There is no harm done in that. All right. So I should, of course, give you some examples. And the first example should justify why this is a reasonable definition. And this means that I should explain to you how you pass from a classical compact metric space to one of these compact quantum metric spaces. And you, of course, choose C of X to be your C-star algebra. And then as your semi-norm, you simply take the Lipschitz constant of a function. And you see, of course, that this does not see whether you take the complex conjugate of the function. So it's star invariant. It vanishes on the identity, of course. And it is finite exactly on the Lipschitz continuous functions. So the Lipschitz continuous functions are well known to be dense. So all of the basic axioms are covered. But what might not be that obvious is that you do get from that a metric which metriizes the weak star topology. But this is actually a classical result due to Kantorovich and Rubinstein from back in the 1950s that this is indeed the case. They were, of course, not thinking about quantum metric spaces back in the day, but since the state space is the same as the probability measures on X, this is a well-studied object, and in that world, this metric is known as the Wasserstein metric. But I should, of course, give you non-commutative examples as well. And here comes one. So if you start out with a spectral triple, and I'm not going to dive into the finer details of the definition of a spectral triple. I presume that most people in the audience know it, but let me just say that the data consists of an algebra, a dense subalgebra, and a C-star algebra, represented concretely on a Hilbert space, and then an unbounded operator on the Hilbert space, which is supposed to interact well with the algebra A. And one of the requirements is that for all elements in this dense subalgebra, this commutator makes sense and is bounded, which of course means that I can take its operator norm and get a number, and this is a semi-norm. And you might now think that I'm going to say that this defines a quantum metric structure, but alas, this is not necessarily the case. It does oftentimes, but not always. And there are several reasons for that. Some are more sophisticated than others, but one of the low-tech issues that could happen, you can very well imagine that your Dirac operator commutes with more than just the identity, and then you of course have a problem. But even if you remedy that, other problems can appear. But in many important examples, this is the case. I mean, the most important and classical example, of course, is the commutative case where D comes from a Dirac operator on a spin manifold, and then it's one of Kohn's initial observations that this recovers that this metric metrizes the weak star topology. But you can also do more non-commutative examples. For instance, you can take the reduced.
Sorry, David, if I may, be still commutative for a while. In this first case, first example, what's the relationship between the metric given by this leap norm and the original metric on X?
They agree.
Okay.
So it is so wonderful that if you embed your metric space as point evaluations in the state space, you recover the original metric from the Wasserstein metric.
I needed to hear it, yes.
Everything is hunky-dory.
Yep.
Yep. So in the non-commutative issue here, the non-commutative instance where you have a C-star algebra arising from a discrete group, if you have a finite generating set for your discrete group, then you can look at the corresponding length function, and out of that you can form a Dirac operator, which simply takes a group element and rescales it by the length. So in some instances you can prove, and it's not trivial, that this gives you a quantum metric structure. You can do it for hyperbolic groups and you can do it for nilpotent groups, but I believe that it is completely open in full generality. I don't know of any counterexamples here. You can also do AF algebras. There you have quite a bit of flexibility. And perhaps more importantly for this talk, you can do it for the Potlusphere. So the Potlusphere has a natural Dirac operator on it. It was constructed by Dabrowski and Syddansk around 2003. And then in 2018, Konrad Aguilar and Jens Kohl proved that this Dirac operator does indeed give rise to a quantum metric structure. And I'll get into the finer details of the Potlusphere a little bit later, but I wanted to address a question that comes up naturally at this point, namely, how on earth does one verify that this metric metrizes the weak star topology? Because this seems like a hard problem to solve. And it is a hard problem, but luckily there is a criterion which is much easier to check, which translates the issue into something of a much more topological nature. So the theorem is also due to Riefel. So imagine that you take one of these operator systems or C-star algebras, and then you take a semi-norm which satisfies all of the requirements, potentially perhaps not without the metrization of the weak star topology. Then the theorem says that you get a quantum metric structure exactly if the semi-norm unit ball projects onto something in the quotient by the scalars, which is totally bounded. And totally bounded here, because we are in a complete metric space, it's just the same as having compact closure. So you can translate this issue into figuring out whether a certain set has compact closure, and this is in almost all instances how one goes about proving that something is a quantum metric space. There is another issue that one could address at this point, namely, why is this the right definition? One could imagine that other definitions could have been equally good, and maybe they are, but one of the major advantages of this setup is that you have a non-commutative analog of the Gromov-Hausdorff distance, known as the quantum Gromov-Hausdorff distance. And I would like to give you some of the details of how one constructs this. So Piotr told me that I should try to sort of aim for a mixed advanced and not so advanced audience. Yeah. So I'm trying to give some of the background details in the beginning, and I promise that I'll get
thank you so much. Yes.
I'll get to the research part soon enough.
I have a silly question. This notation, what does it really mean? What do you mean by X divided or X over C?
I mean the quotient space. So
quotient, really the quotient?
Really the quotient space, and by C I mean C times the unit.
Okay.
Yeah, so really the quotient space with its quotient norm.
But
norm,
X
I take them.
Because X is a complete operator system.
Sure,
okay,
so I take the norm on X, project it down to the quotient space, and there it needs to be compact.
You know what confused me was that I thought of X as a space, and it's not a space.
It's not. Yeah, X was a space a little while
Exactly.
back. So yeah, but from now on, X will not be a classical space, but a quantum space. Yeah.
Sorry.
But But in order, I mean, maybe I should not assume that people are well acquainted with the classical Gromov-Hausdorff distance. So let me start there. So let me tell you a little bit about the classical Gromov-Hausdorff distance. And this is extremely classical. So you start out with a metric space and two subsets therein. And if you look into Hausdorff's Grundzüge der Mengelehre, you will see the following definition. It's the definition of the distance between A and B as subsets of the ambient space X. I realize now that I lied before. Here, X is also a classical space, but soon, I promise, it'll not be a classical space anymore, but only an operator system. So you simply take the smallest r such that one set is contained in an R neighborhood of the other and vice versa. And this is the Hausdorff distance. And to get to the Gromov-Hausdorff distance, this is the issue. This is solving the problem that occurs if your two compact spaces no longer have an ambient metric space within which they sit. So what do you do then? Well, you just build an ambient space. So you look at the disjoint union of the two sets, and then you look at all possible metrics which restrict to the given metrics, and then you measure the Hausdorff distance in the disjoint union. So this is the same as taking the infimum over all possible embeddings into all possible metric spaces. And the reason why I chose this disjoint union version of it is that it tells you quite clearly how you modify this to become a definition which works also for the quantum metric spaces. So this theory of the quantum Gromov-Hausdorff distance is also due to Riefel, and you start out with two of these quantum metric spaces, and the non-commutative version of a disjoint union is a direct sum. So we need to look at non-commutative metrics, aka Lip norms, L on the direct sum, and then we need to mimic this fact that the metric restricted to the two metrics on the original spaces. And this is done by saying that the semi-norm that I get from L by modding out A2 should be the quotient semi-norm I get from L by modding out A2 should be L1. And the semi-norm that I get on A2, the quotient semi-norm that I get by modding out A1 should be A2. And the reason why this works well is because from that, if you dualize things, you get isometric embeddings of the corresponding state spaces. So the state space of A1 embeds isometrically in the state space of the direct sum, and similarly with A2. So now we have classical compact metric spaces which sit in a classical compact metric space, and we can just measure the Hausdorff distance between these state spaces in there. And then we take the infimum over all the possible semi-norms. These semi-norms are called admissible. And this is the Gromov-Hausdorff distance of Riefel between A1 and A2. And there is good reason to call this a distance function because it is clearly symmetric, and it also satisfies the triangle inequality. The latter is not a triviality, but it's true. This was a good news. The bad news is that distance zero might not mean exactly what you would think. Namely, from a classical non-commutative geometry point of view, you would potentially think that this should mean that you have a star isomorphism between the two C-star algebras, which intertwines the semi-norms. But there are various ways of phrasing it. I chose sort of a slightly cheeky but slick way of phrasing it, namely that it can be formulated by saying that it corresponds to an affine isometric isomorphism between the state spaces. And already here you can feel that there is no hope that this should correspond to a star homomorphism, because the state space is completely determined by the self-adjoint elements and the order structure. So the order unit space associated with your C-star algebra gives you all the data needed in order to define the state space. So this is all the data that you are able to recover. There are other versions of this Gromov-Hausdorff distance which take care of this issue. So there's one by Hanfeng Li for C-star algebras. There's one by David Kerr, also for C-star algebras. And then there is a huge body of work due to Frédéric Le Trémolière, and all of these more advanced Gromov-Hausdorff distances have this built-in feature that distance zero actually means star isomorphism at the level of C-star algebras. But we will stick with Riefeld's original definition throughout the talk because it's the most accessible one. And it's already complicated enough for what I'm going to discuss.
Sorry, you said star isomorphism, but also you should somehow like to intertwine this semi-norms, yes?
Yes. So, I mean, in an ideal world, distance zero should mean star isomorphism intertwining the semi-norms. And you can formulate distance zero here by means of an isomorphism of order unit spaces intertwining the semi-norms. Okay, I'm lying ever so slightly, and since Mark is in the audience, I should be careful with that. So you need to do suitable completions before that is true on the nose, but you can do it. Yeah. On the topic of bad news, it is not so that the map or the functor or whatever that sends a compact metric space to its corresponding compact quantum metric space is an isometry. I mean, from the classical Gromov-Hausdorff distance to the quantum ditto, but it is a contraction. So the thing that can happen, and that happens, is that you have two classical spaces of a certain distance classically, but then there is a quantum shortcut between them. So this can happen, but it's not too bad in that it is a homeomorphism. So as far as convergence issues and continuity issues, it doesn't matter whether you view the space classically or quantum. So having such a distance function opens up a wealth of new problems that one can study. Namely, one can try to study the class of compact quantum metric spaces from a much more analytical point of view. You can ask, are two spaces close, or are they far apart, or is the sequence converging or not? And this, of course, has been studied in great detail. And oh, I see that there is a question, maybe? It's a raised hand, yeah? Oh, you need to unmute, I think.
Sorry. Could you come back to the previous page? Yep. It is about this contraction, which is not an isometry. I'm interested, is there a comparison between the Gromov-Hausdorff metric between compact spaces and quantum and their quantum Gromov-Hausdorff distance?
Do you mean if I can bound from below somehow?
Yes.
I don't know. I don't think so. So the counterexample, you can do counterexamples already with finite spaces. So 3-point and 2-point spaces, I think even. And there you can, it's Hanfeng Li who cooked up a counterexample, and you can get distance at least 1 and 2, I think. So I don't think there is much hope to get what would be a bi-Lipschitz map. But I can't give you a concrete sequence which would back up my statement.
But forgetting about the bi-Lipschitz condition, is there a inequality?
Yes, the inequality is exactly coming from this being a contraction. This being a contraction exactly means that the quantum distance is smaller than the classical distance, right?
Okay, thank you.
Right. So this was what I meant by contraction.
Right,
So,
but may I have a question related to this question which was asked?
Absolutely.
So you said that this problem of finding by Lipschitz equivalence could be difficult, and it could in fact be the answer could be negative. But still, is it true that if I have a Cauchy sequence in the range, do I get Cauchy sequence in the domain? You see what I mean? That this this function is somehow uniformly continuous in both directions. On the so this is true, yes.
This is exactly what I tried. Maybe I must have failed completely in my last slide here. So let me try to, because this is exactly what I tried to say by saying that it's a homeomorphism onto its image. So I really mean that convergence, if you take a sequence of classical spaces, then you can ask, whether it converges or not. And you can ask the question classically, and you can ask the question quantum, and the answer is yes or no at the same time.
Yes, but my question is slightly different. I'm
then
asking about the homeomorphism. So, in fact, if you have a homeomorphism, it translates convergent sequence into convergent.
Oh, I think either did I lose connection or did you? Is everybody still there?
Adam lost connection.
Adam lost connection. All right.
If I may, I think I know what he wanted to ask.
Yeah.
Because the part about being homeomorphic onto its image guarantees that convergent sequences are transported into convergent sequences and the other way around. And Adam wanted to ask whether or not a Cauchy sequence is transported into a Cauchy sequence and the other way around, because, well, it's not always the case.
I'm not sure, actually. I'm not sure, actually. If anybody knows, chime in.
Sorry, my connection has.
Yeah. I understood. Someone repeated your questions. I now understood your question, and the answer that I gave was I'm not sure. If anybody in the audience know, then feel free to interrupt.
Okay, and sorry for this.
No worries. I wanted to discuss some continuity results so that you get a flavor for what is known and what is not known. And the most natural place to start, of course, is your most favorite non-commutative space, namely the non-commutative torus. And Riefel proved in one of the early papers that these do indeed vary continuously in the deformation parameter theta. I'm not telling you what the quantum metric structure is here, but you might imagine that it exists. And here is the real claim to fame for the theory, namely Riefel's result also from 2004, which says that these fuzzy spheres, also known as matrix algebras, they converge to the classical two-sphere. So this approximation of the two-sphere by matrix algebras is something that has been going on in physics for a long, long time. And Riefel's result here gives really like a framework within which to formalize this idea. You can do tons of other things. You can do cross products, you can do solenoids, you can do AF algebras. But one thing that was not well understood, at least not up until recently, were these Q-deformed spaces. And the Q-deformed spaces are really at the heart of non-commutative geometry. So we really ought to understand these better from the point of view of non-commutative metric geometry. So let me talk a little bit about Q deformations and get to some convergence result or continuity results for those. So without further ado, let's introduce the main player, which is of course Voronovich's quantum SU2. And most of you know this quite well, but let me just define it, because then I can also sort of at the same time introduce the notation that I'm using. So it's a universal C-star algebra. It has two generators. We call them A and B, and they're of course supposed to have a bunch of relations, and the relations are best summarized by demanding that this 2 by 2 matrix is unitary. And maybe I should comment on the notation a little bit, because I don't know if Adam Skalski is here, but I have provoked him before by using this notation, because in the Warsaw community, you usually call the generators alpha and gamma, and I might even have interchanged the role of the stars here. But we've chosen this because this is the notation that was used in the paper by Dabrowski and Syddansk. And everything we have done since then has been building upon this paper. So we're trying to have a uniform notation throughout the new literature, so that one can read it without having a dictionary available at all times.
Well, David, this is a smart move, because both Dombrowski and Syddansk are in the audience.
Wonderful, wonderful. And Adam Skalski is not?
Adam Skalski is not.
I didn't need to apologize then.
Yeah, exactly.
Anyway, one apology too much is not a big problem, I suppose. But as you all know, I suppose this is a compact quantum group, and if you don't know, it doesn't really matter. But it has a lot of additional structure, and this algebra that I get by not completing the algebra generated by A and B is a Hopf algebra. And I will use the standard Hopf algebra terminology. So delta will be the co-product, S will be the antibode, and epsilon will be the co-unit. And maybe a small comment is in order here, namely that the co-unit here can actually be extended to the entire C-star algebra. This is the fact that quantum SU2 is what is called co-amenable. So later on, you will see this epsilon appearing actually as a state on the whole C-star algebra, and this is allowed because of co-amenability. And quantum SU2, it has a friend, namely the quantum enveloping algebra. So it's denoted UQ-SU2, so it's a deformed version of the standard quantum enveloping Lie algebra. And this guy has also a bunch of generators, E, F, and K is supposed to be invertible, and then there are a bunch of relations. And I've written them down so that you can get a feel for it, but you don't necessarily need to remember these relations. But you still see that there are some Q commutation relations going on. And this beast, this UQ-SU2, interacts well with the coordinate algebra, in the sense that you have a pairing between the two algebras. So this is a pairing of this algebra and that algebra, and it's not only a pairing, it's actually a pairing of Hopf algebras, because this is a Hopf algebra. I didn't tell you why, but it is. This is a Hopf algebra, and it's even a pairing of Hopf star algebra. So there's a lot of structure to this pairing, but you don't need to know too much about the pairing. All you need to know is that from it, you get a left action of one algebra on the other. So this UQ-SU2 acts on the coordinate algebra. So if I take an element in the Lie algebra and one in the coordinate algebra, I need to tell you how this action is defined. And you simply take your element, you co-multiply it, and then you slice with the corresponding functional on the right leg. And because you slice on the right leg, you get a left action. And it doesn't take too much creativity to ask what happens if I slice on the left leg instead. And I do get a right action then. So I have a bimodule structure on the coordinate ring, and the ring that acts is this deformed Lie algebra.
And when you write your one, you actually mean simply identity.
Yes, when I write one, I mean identity. Yes, yes. This is a bad habit of mine, but it plays a role of identity here. So it might be worthwhile paying a little bit attention. So this partial symbol will be the left action, and the delta will be the right action. And I will play around with both throughout the talk. So there's one little ingredient that we still need, namely the action of the unit circle on the C-star algebra. And you can check quite easily that if you just rescale your generators with a complex number, then the rescaled version will satisfy the same axioms, and therefore you get an action of the unit circle. And once you have an action of the unit circle, you get spectral subspaces. So for each integer m, you get the mth spectral subspace, and this is just the elements where your action acts simply by set to the power m multiplied onto your element as a scalar. And it has an algebraic analog because this action preserves the coordinate algebra. So you can also look at the algebraic spectral subspaces. All right.
There is a question.
There's a question. Yes, sorry, I missed it.
Yes, I wanted to ask if this pairing extends to the C-star algebra on the right side.
No, it doesn't. No, this is a pure Hopf phenomenon.
Okay.
You see, Jacek, think about it. This is Lie algebra, so these are vector fields. I mean, you cannot apply a vector field to a continuous function which is not differentiable.
Okay, so that's how I should think about
Exactly.
it.
Yeah.
Vector fields. Yeah.
So that's.
But you're allowed to differentiate polynomials, and this is what we do.
Exactly. Yeah. I mean, you can go further. You can have some Frechet completion, and it would work, but not to the C-star algebra. So C-star is no.
But even Frechet completions is way too complicated for what I'm going to talk about. So I'll stick to the purely algebraic level.
That's fine.
All right.
But these guys, since we are talking non-commutative geometry, so these guys are simply Hopf line bundles. These are finite generated projective modules, which are the section modules of Hopf line bundles.
Yeah, exactly. So I wanted to zoom in on one of the spectral subspaces, which is known as the Potlusphere, because you know, presumably from a course in topology, that the classical two-sphere can be viewed as a quotient of the free sphere, and the free sphere is the same as the classical SU2, and this is called the Hopf vibration. And if you dualize this picture, this means that you can get the continuous functions on the two spheres as a fixed point algebra. And once you see that, you can go non-commutative, so to say, on this definition and define a quantized two sphere by simply taking the fixed point algebra under the circle action that I just discussed. So, i.e., looking at the zeroth spectral subspace. And this is what Piotr Potlusz did, and this is therefore called the Potlusz two-sphere or quantum two-sphere. And if you want to be a little bit more concrete about it, it's actually generated concretely by these two operators. So B star B, where B is from SU2. So this is a self-adjoint guy, and then there is a non-normal guy, capital B, which is A B star. And similarly, I can just look at the algebra that these two generate. So the non-completed algebra, and I'll use the symbol O in this case as well to denote that guy. And the reason why I'm talking about this is that you do actually get that this algebra fits into a spectral triple, an honest to God spectral triple. And this is the Dabrowski-Sittas result from 2003. And once I have a spectral triple, I told you how to form a semi-norm. I can look at this commutator semi-norm. And this does turn the Potlusphere into a compact monometric space. And this was what Jens and Konrad showed back in 2018. They showed a little bit more because they actually extended this semi-norm to a maximal version of it. So even though you're not allowed to differentiate all functions, you can differentiate more than just polynomials. So you can look at the biggest algebra or the biggest space, which turns out to be an algebra, where this commutator is well defined and bounded. So this is the quantum analog of the Lipschitz functions on the Potlusphere, and they proved it for that, the maximal semi-norm. And you see that this is a harder problem than proving it for the other one, because I told you that Riefel's criterion says something about pre-compactness of the unit ball. And if you increase the domain of your semi-norm, you increase its unit ball, and it becomes harder to prove that this projects onto something compact. So this is what they proved, and this was the state of the art in 2018. And we were lucky enough to have Conrad Aguilar join us as a postdoc in Odense in 2020. And because he was there, we set out to prove, or investigate maybe rather, if these quantum spheres, if they vary continuously in Riefel's Gromov-Hausdorff distance. And it took almost a year and a lot of failed attempts, but at the end of the day, we were actually able to prove this. So we were able to prove that even with the maximal semi-norm, the Potluspheres form a continuous path of compact quantum metric spaces. So in particular, this means that as your deformation parameter Q goes to 1, your quantum metric spaces will converge to the classical 2-sphere with its Lipschitz semi-norm coming from the classical round metric that it gets from the embedding into R3. And this is, of course, nice to know, but at some point you need to move on, and the next object of study is SUQ itself, of course. But here you run into trouble in the sense that it doesn't really fit all that well with the axioms of a spectral triple, in that you can define a ton of spectral triples. So there have been, or not spectral triples, but Dirac operators. There are many papers defining Dirac operators on quantum SU2, but they all seem to be flawed in one way or another. So you can sort of play around and get certain things to work, but then you lose other things. And notably, in most cases, you don't even get a spectral triple. And in the cases where you do get a spectral triple, somehow the underlying Hilbert space is a little bit too small to be a suitable spinor bundle. So this is hard. But our hope, and here our means Jens and myself, was that maybe one can squeeze out a quantum metric structure nevertheless from one or several of these Dirac operators. And at that point, you of course need to figure out which Dirac operator to choose. So we are after a Riemannian metric, so it should somehow come from something which is spectral geometric. So it should come from a Dirac type operator. And if you look into the literature on these Dirac operators, you will see that there are at least 2 suitable candidates. They appeared at roughly the same time, and one was by Kuhl and Rogers Sr., and the other one was by Ulrich Krämer, Adam Rennie, and Rogers Sr. And they both seemed amenable to this idea of building a semi-norm out of them. And at the end of the day, we actually settled on treating both of them in that we actually define a 2-parameter family. So we define Dirac operators DTQ, so to say, which has the Q built in, and then an additional parameter T, which is supposed to sort of interpolate between the two candidates, namely the one studied by Kurden Sr. and the one by Krämer, Rennie, and Sr. But I shouldn't postpone the definition too much. I should simply define these Dirac operators. And of course, I need to figure out first what should be my spinor bundle. But in analogy with the classical case, there isn't that much choice. You should take the L2 space of quantum SU2. So quantum SU2 has a designated state, the Haar state. And once you have a state, you can perform the GNS construction, and then you take the GNS space and you double it up. But then you need to start defining your Dirac operators. And I was maybe stretching things a little bit, because we more so define 2 Dirac operators. So we define what we call a horizontal Dirac operator, and it's given by a matrix, a 2x2 matrix on this a direct sum, and its entries are built out of this left action that I get from the quantum enveloping Lie algebra and the concrete formulas you will see up there. And you can see right away that this is not globally defined, but it is at least defined on the dense subspace, which consists of 2 copies of the coordinate ring. So this is the horizontal Dirac, and then it has a corresponding vertical Dirac. It's defined also on 2 copies of the coordinate algebra, but it has this additional parameter t that I was talking about built into it. And it's a little bit more tricky to write down. So I can write it down on vectors which are coming from the direct sum of 2 spectral subspaces. And these exhaust this domain, so it's enough to tell you what it does there. And there it simply acts by a diagonal matrix with scalar values. So this is just the power of the t. And then there is this number in the brackets, and these are the q numbers, or rather here t numbers. So the t number corresponding to a real number a is given by this formula, and this only makes sense, of course, when the t is not 1, and when t is 1, you simply put it equal to the real number. So these are very, very classical objects in the quantum group literature. And it's, of course, concocted in such a way that as t goes to 1, at goes to a. But if you don't like these q numbers and you're not used to them, feel free to zoom in on the case where the t and the q are the same. So in this case, the vertical Dirac operator here also has a sort of more intrinsic description in terms of the quantum enveloping Lie algebra. So the formula is there. So you see that there are some q's floating around, and then you have this generator k to the -2nd power. But this is exactly, when you sum these 2 guys up, this is exactly the Dirac operator that appeared in the paper by Kurdan Sr. in 2012. Yes, there's a question, I think.
Yes.
Yes. So finally, this vertical Dirac operator is scalar. Is this just multiplying by a scalar matrix? Yes, or is it some kind of differential operator?
It's multiplying by a scalar matrix on the direct sum of 2 spectral subspaces. But as I change the spectral subspaces, the scalars vary.
Ah, okay.
Right.
So is it this operator is unbounded? Yes.
It'll be unbounded. Yes.
Okay.
Yeah. I mean, I think if one is not, I mean, I think for the purpose of most of the talk, I think it's enough to think of the case where t and q are the same, in which case you really have this global formula that you can apply.
Okay.
Yeah.
Okay. Thank you.
Oh yeah. So the interpolation issue comes as follows. So if instead of taking t equal to q, you take t equal to 1, you basically, up to small modifications, get the Dirac operator that was studied by Rennie and Senior and Kramer. So we have both of them in the game at the same time.
And any reason for calling one Dirac horizontal and another one vertical?
It's from line bundle theories, or like so it's because one of them corresponds to the base space in the Hopf vibration, and the other one takes care of the circle action. And in that literature, you use vertical and horizontal, sure. So we simply adapted that. Yeah.
Okay. Okay. Thank you. Yeah.
And things are working out well in the sense that these are essentially self-adjoint, so you can construct closed, unbounded operators, which are then self-adjoint. And we denote them by the same symbols, but without the script D. Now, I'd like to talk a little bit about the properties, because you need to understand these Dirac operators a little bit better. And unfortunately, you don't get a spectral triple, but you do get one parameter group of automorphisms so that instead of looking at classical commutators, if you twist by this sigma, so look at expressions of this form, where the parameter in the automorphism corresponds to the parameter in the Dirac operators, then you do get bounded operators, and I denote them by partial V and partial H. And we will use those as well quite a bit. And then you have an SUQ2 equivariance, which is something you would expect. I'm not going to go into the details because it's actually not particularly important, but I wanted to somehow survey some of the main properties. You also have a first order condition. So if you're used to spectral triples, you will know that there is such a thing as a first order condition. And in our setting, this takes a slightly distorted form in that our ordinary commutators are replaced with the twisted commutators, but other than that, things work out. And then you should, of course, make sure that your definition fits with the classical case, and it does, in that if you take your classical free sphere with its classical spin structure and form the classical Dirac operator, you get exactly D11, i.e. the one where both parameters are 1, multiplied by 2 and added 1. All right, maybe I should address the constants here. The added 1 doesn't really matter from the spectral metric point of view, because as soon as you start forming commutators, adding a 1 doesn't matter. But you might think that we had made a mistake, that we should have divided by 2 somewhere to avoid this factor of 2 showing up. But you see, in the Hopf vibration, what actually happens is that the unit free sphere submerges onto the 2 sphere with radius 1/2. So if you want your 2 sphere to have radius 1, you should multiply the radius of your free sphere by 2. And this is exactly the 2 that pops up here. All right. So I was after quantum metric structures. So I should tell you how you can define them from these twisted derivation as they turn out to be. So this partial H and partial V are twisted derivations in that they satisfy a twisted Leibniz rule. So I just need to remove this bar because it's making me not being able to see my own slides. Oops. Okay. Hide floating panels. Thank you. So you have a twisted Leibniz rule where the twist that appears are exactly these automorphisms that were defining the twisted commutator, and you have a similar one for the vertical one. So I wanted to build a semi-norm out of these guys, and what you can do is, of course, you can look at these bounded twisted commutators, then you can add them up, then you get a new bounded operator, and you can take the norm. And then you can simply define the semi-norm to be infinity outside of that. And this makes sense. And if you want to, you can actually start wondering, can you ever compute this quantity underneath the norm sign? And you can, because you can actually figure out a concrete formula, so you can express this sum in terms of the deformed Lie algebra as well. So you have a very concrete formula that you can use to compute with. And this is somehow, hopefully, I think, indicating that this is a reasonable object, because it's both somehow coming from a Dirac type operator and at the same time very much related to the Q geometry coming from the deformed Lie algebra. And very much like the Potlusphere case, it also has like a maximal version. You might imagine that it has sort of a maximal domain upon which these things are defined. And I will denote this domain by lib_t. So this is our substitute for the Lipschitz functions on the quantum SU2. And before I continue, I should make a comment, namely, it can be proven that this map here, the sum of the derivations, that this is actually closable. And it is extremely tempting at this point to think, oh, well, if you pass to the closure, you probably get the maximal semi-norm. But this is not the case. So passing to the closure is a reasonably easy process to control from the quantum metric point of view, but passing all the way up to the maximal domain is another kettle of fish. So the difference classically corresponds to passing from polynomials to C1 functions, and then there is a huge gap between the C1 functions to the Lipschitz function. So you need to do a lot more careful analysis if you want to treat this maximal semi-norm. But there's of course no need to be intimidated by its maximality. The question that you of course should ask at this point is, do you get a quantometric structure from this maximal semi-norm? And if you do, then you're good, because then you automatically get it from the minimal one as well. So how would one go about proving such a thing? Well, what you can do is that you can look at the restriction of your semi-norm all the way down to the Potlusphere. And what turns out to be the case is that you recapture exactly the semi-norm coming from the Dabrowski-Sitar spectral triple, which means that since we know that this gives the Potlusphere a quantometric structure, we at least get a quantum metric subspace of my potential quantometric space. And as Piotr already pointed out, these spectral subspaces, they're actually projective modules over the Potlusphere. So if you sum up a bunch of them from say -m up to m, you do get an operator system. It becomes star invariant, and it becomes a module over the Potlusphere, and it becomes a finitely generated projective module over the Potlusphere.
In fact, it's free.
In fact, it's free. Is that the case?
Yeah, because you sum from -m to m. Yeah.
Yes. So even though, each spectral subspace is not free.
Exactly, which you can prove by index pairing.
Is free. Yes. Yes, that's true. That's true. But the question, of course, is then, is it possible to induce the quantometric structure up to a finitely generated projective modules? And if you do your mathematical push-ups for long enough, you will see that this can indeed be done. So we can prove that these spectral subspaces, these spectral bands rather, are compact quantometric spaces. Okay, so now we have pushed a little bit the problem in that we have passed from the Potlusphere all the way up to the spectral bands. But the question is, of course, how do we get all the way up to quantum SU2?
Yeah.
And for that, you need a little bit more work. And I'm gonna give you the result that we're using, because I want to somehow advertise that along the way we are developing quite a bit of technology. So the little lemma says that if you have something that you're really hoping would be a compact quantometric space, so an X and an L, and if you have maps from it into something that you know is a compact quantometric space, and also have a map backwards from the compact quantometric space into your X in such a way that, well, the first map up here is supposed to be bounded for the semi-norms, and then it is supposed to approximate the identity better and better on the semi-norm unit ball. If you can do that so that you approximate for every epsilon the identity map on the semi-norm unit ball, then your original space was also a compact quantometric space. And this is the lemma that we are going to apply here. So we simply construct a bunch of, they're actually going to be lib norm contractions or semi-norm contractions onto the spectral bands, and we can control them on the Lipschitz unit ball by means of a sequence which tends to 0 as m goes to infinity. And therefore, those in combination with the lemma up there gives you that for every T and Q, you get a quantum metric structure on quantum SU2. And you might wonder what these EMs are. The most natural thing is to just take the projection onto the spectral band. It turns out not to work. You need to somehow smoothen it. So you take a weighted average of the projections onto the spectral subspaces that appear in the spectral band that you're looking at. All right.
So David, just a silly question.
Sure.
So now by your lemma, you have that XL is a compact quantum metric space. So now can you also say as a kind of corollary that psi E becomes semi-norm bounded for a semi-norm L?
Can you say that? I am not 100% sure, but I would think so somehow, right? Because
yeah, it looks, you know, for symmetry reasons, you know.
Yeah, I'm only looking at the inclusion. Of course, my psi is just the inclusion, so it's not something that I'm particularly worried about in this concrete instance. But
you see, this is a very general statement. There exists A. I mean, it can be anything, right?
Sure. Yeah. All right. So knowing now that you have quantum metric spaces, you need to address the question of continuity. So you need to ask, is it actually so that these quantum metric spaces vary continuously as the two parameters T and Q vary? Now, for this, in order to sort of have a point of attack to this issue, you need fuzzy approximations. And this is something that goes back to Riefel's original work. And we figured out already in our paper on the Potlusphere how to do quantum fuzzy spheres, so to say. So you can write down concretely a sequence of so-called fuzzy quantum spheres or quantum fuzzy spheres. I haven't really settled on the order of the adjectives. And you simply take a span of polynomial expressions in these generators A and B. So if you have them for the Potlusphere, it's very tempting to try and push these into the spectral subspaces. And one way that you can push them into a spectral subspace, say AM, is by taking these finite dimensional spaces and then multiplying them by polynomials of this form A to the K times B to the M minus K, because these are generic elements in, or not generic elements, but obvious elements in the AQM. So here you get a finite dimensional subspace in AQM. And if your M is negative, you need to add some stars, but it's basically the same definition. And then you can sum all of these up and call them a fuzzy analog of the spectral band. So you just sum from minus M to M again, these pushed spectral, these pushed fuzzy quantum spheres. And you can prove that this fuzzy spectral band is an operator system. And it's also easy to check because of finite dimensionality that these are also sub-quantum metric spaces. So in order to get these into the game, you need to somehow find a way of approximating quantum SU2 with these fuzzy spectral bands. And I'm going for a couple of slides now to restrict to the case when T and Q are the same number, because this will make some of the arguments quite a bit easier. And I think I'm also slowly running out of time in a not too distant future, so I should certainly not push for more complexity here. So we are looking at the case where T and Q are the same. And then you have these finite dimensional fuzzy guys, one for each N and one for each M. And then you have your parameter Q that is still varying. And it's not easy it's not difficult to see that if you fix your N and your M and let your Q vary, these will vary continuously because they're finite dimensional. So this basically follows from the fact that quantum SU2 fits into a continuous field of C-star algebras. So if you have a fixed n and m, you can move your q just a little bit, and the corresponding fuzzy spectral bands will not move too much. So now I need to somehow approximate quantum SU2 with the fuzzy spectral bands. And in order to do that, I need another little piece of technology, namely the following proposition, which says that if I have a compact quantum metric space, and inside of it a sub-compact quantum metric space, then I want a condition that ensures that y is close to x. And the condition is as follows. You're supposed to have a unital contraction from the big space down to the small space. And then you fix an epsilon bigger than 0, and you assume that your contraction is also a Lipschitz contraction, and that it approximates the identity up to epsilon on the Lipschitz unit ball. And then the proposition ensures that y and x are only epsilon apart. So this is the proposition that we're going to use in order to approximate quantum SU2 with the spectral bands, the fuzzy spectral bands. All right, so we need to construct such a beta, and we need to construct one for each n and one for each n and m onto these fuzzy spectral bands, or into them at least. So how does one go about this? Well, looking into the literature, such a map is known as a Beretson transform. So we are going to define a quantum Beretson transform in our setting. And what one does is one constructs a family of states, one for each n and one for each m. And then this beta in m is supposed to be a slice of the co-multiplication on the right leg with this state. So this is at least unital and contractive. Actually it's a complete contraction. And these chi-and-m's are chosen in such a way that they converge to epsilon to the co-unit in the weak star topology. And because of that, it's not difficult to imagine that these beta and m's approximate the identity map, because if you plug in an epsilon there, you get the identity map because of the co-unit property. So what is much more worrying is whether these should be lip norm contractions, because this twisted derivation that I used to define the semi-norm was given by these partials, and the partials were constructed exactly by slicing on the same leg. So one should be extremely skeptical at this point, because there is no reason why I should be able to move a beta past that partial, so to say. But here comes the small miracle, and the reason, one of the reasons why I zoomed in on t equal q, namely, if you take this matrix consisting of all these partials and conjugate it with the fundamental unitary, then you get exactly the same matrix, but all of your partials are turned into deltas. So exactly this formula holds. You just replace all your partials by deltas, and then you have something which is defined exclusively by slicing on the left leg. And clearly this guy, this delta guy, defines the same semi-norm, because I just conjugated by a unitary and I'm applying the norm anyway. So it gives you back exactly the same semi-norm. And now I can prove that my beta NM is a lip norm contraction, because imagine that I apply it to an element and then take the semi-norm. Well, then I might as well use this delta matrix to compute the semi-norm. But the delta matrix and the betas commute. So now the beta here is applied to every single entry in the delta matrix. But my beta was a complete contraction, so it doesn't matter whether I amplified to 2 by 2 matrices. It's still contractive. So this is then smaller than the norm of the delta matrix, which defines the lip norm. So everything works out, but this little lemma is exactly what saves the day.
Mm-hmm.
Okay. So how are we doing on time?
You have 21 minutes. 20 minutes.
That is more than sufficient. More than sufficient. So what does one gain from such a Berezin transform here? Well, once the dust settles, it turns out that it doesn't really matter whether you look at the maximal or the minimal semi-norm, because they give you the same quantometric structure in the following sense that at the level of state spaces, they actually define on the nose the same metric. So it doesn't matter whether you enlarge your unit volume. And from the quantometric point of view, the distance between the two quantometric spaces that you get is 0. And this is actually quite easy to prove at this point. So let me give you the short argument for the distance 0 result. So I'm going to do it just diagrammatically. So you have your fuzzy spectral bands with the maximal semi-norm. And because of this little proposition and the Berezin transform, these will converge as n and m go to infinity to quantum SU2 with the maximal semi-norm.
Mm-hmm.
But these fuzzy bands, they live entirely in the coordinate algebra. So whether I look at the maximal or minimal semi-norm, it doesn't matter. They agree on the coordinate algebra. So this fuzzy quantum space is exactly the same as this fuzzy quantum space. And then you can play the same game and see that the fuzzy bands with the minimal semi-norm converge to the quantum SU2 with the minimal semi-norm. So at the end of the day, the same sequence converges to 2 a priori different points, but this means that the distance between the a priori different points is 0. So this is somehow a reduction result, which tells you that if you want to study the continuity question, you can dispense from quite a bit of analysis because you don't need to deal with the maximal semi-norm. You can just work exclusively with the minimal one, and all continuity results holding for the minimal one will then automatically hold for the maximum one because the distance is 0. Okay. So having this, we are actually in shape to attack the continuity problem. And there's one hard problem left, and I'm not gonna go into the details of how to solve it, but the hard problem is to prove that this epsilon that appeared when the beta and m's were approximating the identity map, that they can be chosen locally uniformly. So if you give me a Q0, I'm supposed to be able to control the Berezin transform up against the identity map, up against a fixed epsilon locally around the Q0. And this requires analysis. So you need to work hard to get this, but it's actually true. But once you have that, the whole thing falls apart in that you get the quantum Gromov-Hausdorff continuity almost for free now. So so the theorem says that these quantometric spaces, they vary continuously as Q varies in 0, 1, because I have zoomed in on the case where T and Q are equal, so I only have one parameter in the game right now. So I'm going to sketch the proof, but I'm going to sketch it very, I'm going to draw the proof rather. So imagine that you're given Q0, and then you look at SUQ2, which sits at a different fiber, Q, and you want to show that this guy is close to that guy when Q and Q0 are close. So if you're given an epsilon, then at the fiber Q, if you choose your N and M big enough, you can pass down to the fuzzy spectral bands, losing only an epsilon in quantum Gromov-Hausdorff distance. But because these fuzzy bands are finite dimensional, we saw already that when you start moving in your fiber, you get something which varies continuously. So as if Q is chosen close enough to Q0, the fuzzy band is as close as I wish, within an epsilon, say, to the fuzzy band at the fiber Q0. And then this locally uniformity up here ensures me that if I move like that, I don't lose more than an epsilon over at the fiber Q0, and in total I've lost maybe 3 epsilon, but this is as good as 1 epsilon. So in total I'm within an epsilon of SU Q02. So the hard analysis really lies in getting this estimate up there, but I don't think there's any need to go into the analysis at this point. Maybe a last remark is that all of this stuff also works in the more generic case when you have both the T and the Q. So the real statement is that we get a 2-parameter family of quantum metric spaces which vary continuously in the quantum Gromov-Hausdorff distance, and if you stick to the diagonal, you get the spectral geometry coming from the Koszenia-Dirac operator, and if you stick to the vertical line up at 1, you get the Krämer-Renyi-Stignat geometry, and everything, of course, converges to the classical SU2 with the round metric coming from the free sphere rescaled with a factor of 2 as it ought to be. All right, so this was what I wanted to say. So thank you so much for your attention.
Thank you so much. And I suggest we continue with questions. Mark, any question or comment?
And will the paper appear?
Oh, I've seen people make promises in these situations that didn't turn out to be true, but I'm going to be bold, even though I'm being recorded. I think it'll be out next week. We're typing it up and we are really far along, but it's a beast of a paper. I should warn you already. It has grown and grown and grown, and I think it's approaching 90 pages.
Wow.
So it takes a while to read it, but yeah, maybe we should have sliced it up into smaller pieces, but the whole story is really connected. So yeah, for now, it's one big paper.
I look forward to looking at it.
Thank you. Thank you. And any points of critique or comments is most valuable. So don't hold back. Send us an email if you spot anything that interests you.
Okay, we have 3 people asking questions. So Adam, go ahead first.
Yes, so I have a very general question. How this theory of Gromov-Hausdorff distance quantum, Gromov-Hausdorff distances, deformations in your context fits into the theory of deformation quantization, where instead of Q you have H bar?
Oh, I don't think that it fits at the moment. I don't think I've seen any papers that sort of merge the two. Is that, I'm sure that Mark has plowed through all of the literature. So what do you say?
H bar deformation quantization. That's what leads to the ordinary fuzzy spheres, the matrix algebras. If you're starting with classical.
All right. Yeah, I'm not aware of any direct connections.
So how should we think about this deformation parameter Q? Is this something like e to the power h bar, or?
Yes.
I think it's like I h bar, where
Yes, e to
I
the
is imaginary.
But in this deformation quantization setting, h tends to 0, yes, and here q tends to 1.
Yeah.
So there should be something like exponential, yes?
Yeah. You should. It really is. You should think of it as e to the I h bar should be your.
Okay. E to the power I h bar. Okay, thank you.
Jacek?
Can I ask you to go to the page 17?
Yes. It takes a little while. I'm now regretting all these layers.
But 16 already.
17.
Yeah.
Yes, you mentioned here that this contractions EM are not only projections, but they are somehow smoothed. Could you comment on what is the smoothing? And
you sort of do a weighted average. So you need you have let me see if I can do it without giving you any formulas. So rather than doing this, you do this, right? So when you get far out in your spectral band, sort of close to the capital M, you multiply your spectral projection with something which is roughly like 1 over capital M. And then when you get to the diagonal, you don't do anything. You multiply by 1. Does that make sense?
Yes, it does. But so is this, are this number kind of special? And what probably I really want to ask is it related to amenability or commonability of SUQ2?
I don't think so. So they are the ones that worked. And I can tell you why they are chosen so. It's because it's actually not at all easy to show that this becomes a Lipschitz contraction. It's quite easy to show that it commutes with this partial guy that defines the semi-norm, but it's not easy to see that EM is a contraction, you see. And what we're doing is we are realizing this guy, this EM, as a Schur multiplier. And then you can apply the theory of Schur multipliers to show that it becomes a completely bounded map. And the reason why it's cooked up like that is exactly so that this standard criterion for estimating, so there's a standard criterion due to Grothendieck on how to estimate the CB norm of a Schur multiplier, and we applied that.
Okay, thank you very much.
You're welcome.
Okay, Łukasz, it's your turn.
Okay, thank you very much. I'd like to ask about both slide 20 and 23, if I remember, because because we have here the horizontal and vertical partials. And if I remember correctly, the vertical one was defined only locally, but when T was equal to Q, you were able to give the global formula for it. And then later on, you said that, well, here you said that thanks to this global representation, you were able to switch partials and deltas with each other. But at the very end, you say that this continuity property also works in general case. Could you tell something more how you dealt with it? Were you working more locally? Because, well, it seems mysterious, at least.
I understand, but it is at this, I haven't really given any details, so there's a good reason why it seems mysterious, but you see somehow, all right, so the thing that makes it work is that even if you have a general TQ situation, then the Berezin transform approximates the identity. And the identity, of course, commutes with the Berezin transform. So you somehow need to do a slightly more careful approximation argument where you use the fact that you can pass them through each other on the nose when T and Q are the same, and that you get and that the Berezin transform approximates the identity map. It becomes quite a bit more technical, and some of these more general theory results that I mentioned, you also need to soup them up in order to deal with the more general case. But I decided to strip the talk for all its technicalities.
Thank you.
Not all of them. Presumably, some think that it's reasonably technical.
The more nefarious parts, yeah. Because I was only, curious whether or not this is only for the diagonal, and then there was this lemma that epsilon can be chosen uniformly, and that it generalizes from the one-dimensional neighborhood of Q0 to two-dimensional neighborhood of Q0 to T0.
Yeah, you really need to work there. Like you need to work hard there.
Okay. Thank you.
You're welcome.
Tomek? Unmute.
Okay, I have two questions. Both are about shapes. So first of all, I don't have a good intuition about the shape of finite probability measures with Kantorovich metric. For instance, if you consider a space consisting of 3 points, you were talking about, as answering my first question. Is this Kantorovich metric closer to, in the Gromov distance, Gromov-Hausdorff distance, closer to a hyperbolic or flat or spherical triangle? What is the shape of this matrix?
That I don't know. I have probably as little intuition as do you. So since I'm being recorded, I will not make any bombastic statements.
Okay. Okay. So the question
on a finite set of points, I think there's a tremendous amount of variety, and it's related to the transportation problem.
Yes, I know the definition of the Kantorovich metric and this mechanism of generating this metric, but the resulting shape of this space, since I have a way of comparing shapes having this Gromov-Hausdorff space, Gromov-Hausdorff metric, I can ask if some shapes are closer or some farther from a given shape. Okay, so knowing this, that it is this shape is similar to some standard shape, would say something about the shape of this space. My second question is also about the shape, but of SUQ2. Because if you have a fuzzy sphere approximation, then essentially it is built with SU2 symmetry. This matrix approximation comes from representation theory, essentially. So this symmetry is built in this approximation, and somehow it's responsible for some roundness of the limiting metric. What about your approximations? You have this square of these approximations with some diagonal, with some far regions. What about the shape? How the shape of SUQ2 changes if you tend to the classical case from different sectors of this diagram?
I don't know, but I can tell you that our fuzzy approximations are co-invariant for the action of the Hopf algebra. So that should account for some quantum roundness, whatever that's supposed to mean. But other than that, I don't think that I can say much about the shape of quantum SU2. It would be interesting to try and, I think that there are, and maybe I'm digressing, so if I'm not answering your question, then just tell me. I think that Walter van Zeulenkamp has some programs that he's using to draw basically some of the state spaces with their metrics. So maybe one could
I have to find
look for something in that direction, but I haven't even tried. So what you can do is, here's what you can do. You can look at the C-star algebra that is generated by B star B. So this is a commutative C-star algebra with a discrete spectrum. And this is just a sequence of powers of Q, and it converges to 0. So it's like a quantized unit interval. And on that C-star algebra, you can write down a concrete formula for the metric. And we've done that. This is actually what we do. So this is sort of like a bootstrap exercise. So in our very first paper, we dealt with these quantized intervals and how they converge to the classical unit interval. And what we used there was that you could really write down a formula for the metric that you get from the Dirac operator. Then we use that to pass to the Potlusphere. And then we use the Potlusphere to pass to the projective modules. And then we use the projective module to pass to quantum SU2.
Very nice.
Was that an answer?
Yes. I will dig in the literature. Now I know that there is
start from the beginning if you want geometric intuition. Then we start with the quantized intervals, because then there you can really write it down.
Okay, thank you very much. I have one question more. If you have some deformations of Potluspheres, you can get in some limits some singularities, like teardrops, singularities. If you change your parameters in your family, can you obtain some singular shapes?
I don't know. So are you thinking about these generalized Potluspheres where you have like is it a negative parameters C or something like that? Is that what you're thinking about?
Well, you can rescale it most conveniently to run from 0 to 1. It's just a question. Potlush wrote capital C and it would vary to infinity, but it's just a bad choice of generators, right? But indeed, we really have a whole family of Potlush quantum spheres. And you do use 2 parameters. So I wanted to ask this question actually. So when you write this S2 QS, say, Potlush would be QC, whatever, right? And do we have continuity in both of these parameters? Everything is inside SUQ2.
I know. I should start feeling really bad by now, because you asked me the same question a year ago when I was talking about the Potlusphere result. and I said this would be something to look into.
Uh-huh.
And then I got sucked into Quantum SU2 for a full year.
Uh-huh.
And I'm only coming out of that project now. And my answer, unfortunately, is going to be exactly the same as it was a year ago or 2 years ago, or whenever I gave the talk. I haven't had time, but one should certainly look into that. And another thing that someone, maybe not me, but someone should look into is all this continuity business. Can you do that also for the more sophisticated quantum Gromov-Hausdorff distance, so La Tremolaire's propinquity? So, like, I mean, this would be a stronger result, of course.
Yes.
And I don't know. I also haven't thought about it. So I'm not saying that this is a very hard problem to attack. I just haven't done it. But it might be very hard. I'm not sure. I'm not even sure about the complexity of the problem.
Is Frederick here? Frederick, are you here? Okay, no. Okay, so maybe Ludwig first, because yeah, he didn't ask a question yet.
Okay, hi. I have a question, but I had some interruptions, so I'm not quite sure if there will be a really pertinent question. But you said you were not in the beginning not much interested in spectral triples, but then there were during your talk. So do we have really a spectral triple, or at least modular twisted spectral triple on SUQ2, or not yet? So perhaps maybe you said this, but I missed your statement.
So I don't remember the exact.
You have bounded commutators. You have your, well, actually, by the way, this vertical and basic, the horizontal, come from a paper with Syddansk, Andrzej Syddansk, some time ago. We didn't manage to do the SUQ2 as a U1 bundle over Potlusphere because we tried to get really spectral triples, not twisted spectral triples. And perhaps you twisted modular spectral triple. I don't know. Can you confirm this or disconfirm?
Yeah, I don't. Is there a complete consensus about what a modular spectral triple is? Because if so, I don't know the axioms by heart.
Well, you have just twisted bounded commutators with the elements of the algebra, at least dense subalgebra.
So ordinary bounded, not taking
unbounded
plain
commutators. Yeah.
Plain commutators.
Are unbounded.
So you can do. There are genuine spectral triples. So there is one. So Chakraborty and Pell has a genuine spectral triple built on SUQ2, but the problem is that it's acting on one copy of the L2 space, so somehow the spinor bundle is too small. And another thing you can do, and I should have mentioned that earlier, is that you can construct, so you can change your point of view. So you can look, instead of looking at quantum SU2 as a quantum Lie group, you can look at its discrete dual. And then you can look at a length function on the discrete dual, and then you can build, very much like in the discrete group C-star algebra case, a genuine spectral triple out of that. This was done by Bovmik, Vogt, and Zacharias, and you actually get a quantometric structure out of that. It just seems to be more of a discrete kind of situation and not necessarily that related to the underlying geometry. But you do actually get a quantometric structure out of that. I'm not sure if I answered your question. If not, just shoot back.
Well, okay, maybe just one auxiliary question. So your commutator, your Dirac operator builds on the horizontal vertical one. Does it has compact resolvent? Is it correct? Yeah.
No. So in the case where T is equal to Q, it takes the resolvent somehow is compact relative to a type, to a von Neumann algebra. but no, it doesn't. Is the short answer. But there's this paper by Roger Senior and Jens Kuhl where they somehow show to what extent you get a compact resolvent, but you need to change your notion of compactness.
Adam?
Okay, thanks.
Yes, so I would like to come back to my previous question, since I'm a little bit unhappy with this Q being e to the power IH. So H is always real in those consideration about deformation quantization. Therefore, e to the power IH should be something of modulus 1, of absolute value 1. But here Q tends to 1 from the left.
That's
strictly yes, it's the real parameter. So I'm a little bit confused.
Yeah.
What is the relation?
All right. Okay. So you're right. So you get if you of course you get a number on the unit circle. Do that. So so I think you need to do like a logarithm of some point at some point instead. So so for me, the parameter Q is the natural starting point. This is why I'm hesitating here. So
yes, but we agree on the fact that we get classical case if Q is 1 and H bar is 0. Yes, this is standard. Yes.
Yes, but the deformed Lie algebra situation is actually a little bit tricky, because if you put Q equal to 1 in the definition of the deformed Lie algebra, you don't get the classical one. You need to artificially add the H generator of the enveloping Lie algebra. And the H generator, I don't remember the exact formula, but the H should be exactly an exponential of a logarithm of k maybe divided by 2 or something like that.
Okay.
Yeah.
Okay, thank you.
But Adam, maybe it would make you happy if there is at a certain moment a mention of Mark's result about continuity with respect to this irrational rotation parameter for quantum torus. And that definitely is a unitary parameter. So that's really
yes. Okay.
deformation quantization, right, picture. Here you really have this e to 2
with this
pi
correspondence e to the power. Okay,
yeah.
I see.
And
so the deformation parameter in the quantum sphere family is different. In fact,
yes.
We should think it as a different parameter than in this quantum tori. Yes.
Yeah, exactly. Yeah.
Okay. Okay. Yeah. Thank you.
But you can, well, I mean, we can go on forever asking such continuity questions, because, for instance, we have a Matsumoto quantum sphere. And if you take its first incarnation, when it's really, really like this non-commutative torus, I mean, it's kind of built out of non-commutative tori. But then there is also another incarnation where basically what happens is that your theta is no longer a number. It's simply a self-adjoint element of your C-star algebra. So basically, your deformation parameter is a continuous function. And then again, you can ask, well, is it now continuous in the sense of this compact quantum metric topology when you vary your parameter, which is now being a continuous function? So you can go on forever with such questions, right?
Yes, but my question is motivated by the fact that in this case of deformation quantization, there is a precise interpretation of this parameter, h bar, which is very concrete. And in this story about quantum sphere, okay, it fits nicely, but somehow this interpretation is not so clear, yes? as is for a deformation quantization.
But what interpretation do you have in mind? I mean,
some physical interpretation.
Ah, physical, okay.
H bar is something which is fundamentally quantum, yes.
Yeah.
Okay. Yeah.
Planck constant, yes.
I will also refrain from making statements about physics. When
okay.
Why?
You know why, of all people.
Oh.
Okay, anybody else? I don't see any raised hands. Okay, so if everybody is happy, let's thank David again. Thank you so much. This was a very, very beautiful talk and perfect timing. So let me stop recording now.